And let's hope the streaming works right. But if it doesn't, it doesn't. Everybody loves the logistics slide. I think there's more people here tonight than there was last Thursday. Wow. Last Thursday was definitely the low occupancy. Nothing's changed here. Jonas had an emergency, so he is not available in person. He's going to do his office hours on Discord. And he did post on Piazza about that as well, but nobody reads Piazza because Piazza sucks. Nothing else changed there. There's actually not a huge amount of activity going on here. Your implementation report is due this evening, 1 minute before midnight. I mean, you're all well rested because, of course, you just took the last 3 or 5 days off because you took a break, right? Right? Well, if you didn't, you should have. Next week, you have status report. Capstone status report is due on Tuesday, unlike this week where it was shifted out to Thursday. We're going to go back to the Tuesday deadline. Peer review implementation reports are due on Thursday. And there is no self-assessment activity. Today's lecture is just interesting, but I'm not going to expect that you think about it for the final. I don't care that much about it. I think it's a fun topic, and I've talked about some of the things from it before, but now I'm going to be using more of these kinds of lectures. I think we've covered lots and lots of material. There's plenty of stuff to go over on for the final, which we will be doing. Here, nothing else interesting. All right, so today's failure is one that I just got messaged to me, I think yesterday. So I was like, oh, this is kind of cool because it's somebody who took the class last term. That would be winter 2022, term 2. Because UBC only has winter terms because I think that's our coping mechanism for claiming that we're in Canada when we have the most mild of weather. So we just say, no, we've got this long winter and this short summer. As opposed to the rest of the world where they'd call it fall and spring. I mean, and I went to university in Chicago where I can tell you that winter there is way colder than here, and it was still fall and spring. Actually, I think we had a winter term as well. It was a quarter system. So I guess it was 2 days ago then. So, and this is verbatim what they said. Last month, I literally witnessed a failure of the day scenario occurring live in my company. Our product suffered an outage due to replicate database lagging behind to the point where commits were locked up. I hate when that happens. So this stuff really does happen. I did poke them and say, can you point me at something that talks more about this in greater detail, but I didn't get anything back. I'm not super surprised. A lot of people are not comfortable about talking about these kinds of failures. It's rare. The big companies do actually talk about it because it is a learning experience and it's part of their transparency model. Even so, I just saw a really cool blog post where somebody was talking about and comparing Amazon, Microsoft, and Google and their transparency. And they were talking about the different approaches that each company takes to this. Microsoft is apparently very transparent, but they don't leave things up for that long. Usually after a couple of weeks, they take incident reports down. Google and Amazon apparently are much less transparent. That they don't report nearly as many things nor as much detail as Microsoft. I thought the second comment was also very telling. We're trying to deal with our high database load with sharding. So the concepts you taught is playing out in front of me. I think that should be R playing out in front of me, but there you go, authenticity. Real world, things break. Techniques we're talking about are things that you can use to help fix various issues. As I was saying earlier, the time to fix it is when you design it. The worst or most expensive time to fix this is when it's in production. Converting a database from a replicated state system to a sharded replicated system is a big, big change. And doing that without having the whole thing fall apart is a very challenging project. That would make an interesting capstone idea. How do you take an existing in-production database and convert it to a sharded, replicated, in-production database without compromising your service guarantees? Anybody think that's easy? Anybody think it's hard? A couple people are willing to give me, yeah, well, you know, might take 2 or 3 days. I don't know. Maybe some of you just haven't recovered from that break. How many of you actually spent the entire break working? How many of you spent the time gaming? Yeah. You know, sometimes you just have to step away from the problem. Today's conversation is verbatim one that I used last term, and the slides are heavily borrowed from the W23T1 class at Georgia Tech, with permission. This is one of the topics, peer-to-peer and mobility. So the idea is that an extreme example of distributed systems are in fact large peer-to-peer networks, particularly when it comes to mobile devices. Many of the techniques that we have been talking about become very important when we start trying to scale out. I picked on Cloudflare a couple of times because Cloudflare has been stumbling lately. But Cloudflare provides a very important real service in exactly this space. When I start talking to people who are working in, my friend who works in the metaverse, he's doing open standards for metaverse, so that way you can actually have your shiny virtual sneakers appear correctly in a different metaverse. I wish I was making this stuff up. It was actually interesting. You know, how do you make these things interoperate? Because until they can interoperate, it's just a game. And he talked about, I mean, one of the reasons we were talking, because of course I do a lot of storage work, and we talked, and I've told him about my research, and we talked about the need to be able to quickly find objects, assets, or what they're usually called in space, in games. To quickly find assets that are as good a fit for what you need as possible. And it's a really complex problem. He said that a single asset may have as many as 3 different formats, and then each of those formats may have as many as a couple of 100 different variations, so quality levels and versions. And they're not all stored centrally. They're actually stored in a decentralized fashion. So if you're sitting there playing a game with someone else and they have a copy of the asset you need, literally the model is they'll give it to you because they're the cheapest place for you to get it from. There's a lot of interesting trade-offs here. You have to decide what's the least expensive place for me to get that asset from. And that's not just a network decision, it's also a computational decision. Because if somebody has a very low-res version of that, but I need a high-res version, if I do that, I'm going to compromise the quality of your image. On the flip side, if what I have is something I'm rendering way off in the distance, but all that you have local to you is a really big version of it, i.e. high resolution, you're going to spend a bunch of CPU cycles to scale it. So there are a lot of interesting factors that go into it. And I said, wow, this is a much harder problem than I would have thought. And he said, yes. And he says, most people aren't really working on this problem yet. So a lot of what goes on in these kinds of systems is we need to have lots of abstractions because we're trying to move away from the underlying infrastructure. You don't care if you're running on an IPv4 network or an IPv6 network or something very disgusting down here. Smells like hand sanitizer, scented hand sanitizer, lilac scented hand sanitizer. So we try to abstract things away. We have namespaces that we use to containerize the naming that we're using so that we can have overlapping names. We can use the same names over and over again because they exist in different containers, different namespaces. We separate things out at the network level. We often have multiple layers of networking that we're performing because think about mobility. Think about your device. As you move from cell tower to cell tower, your IP address keeps changing. It's not the same. And we can change your network address or we can change the routing to your network address. But things keep changing underneath you. And most of the time, you don't care. You want this abstraction to be transparent enough that you don't actually see these switchovers. We use metadata services and create overlay networks. We separate into logical networks. There's a whole concept in IP, well, actually in Ethernet, called virtual LANs. You can take a single physical LAN and you can actually put multiple different networks on top of it. Logically, I need to not stand over here, obviously. Logically, we're just extending the same idea, which is we have this big universe of networks, and we're going to hide things in a way that allows us to layer them. This is what network address translation does. How many of you have an IP router at home that performs network address translation? You have one. Everyone does. See, it turns out that while 32 bits of IP addresses sounds like an awful lot, less than half of them are useful. Half of them are multicast addresses. Well, no, that's not quite true. It's complicated. Less than half of them are actually usable. And they knew this was a problem many, many years ago, decades ago, and a UBC graduate helped build the solution to that, which was IP version 6, which was instead of having a 32-bit address space, having a 128-bit address space. I don't really care much about that, but then people figured out that they could continue expanding the 32-bit address space by just reusing it and hiding the fact that they were reusing it. So you put a network address translation layer in there. Internally, everything inside of the NAT control zone has a range of IP addresses that are not available for use on the internet. That's how they solved it. They said, we're going to take pieces of this address space and we're going to reserve them. So you'll see a couple of these. 192.168 is a Class C address. 172 is the Class B address. And 10 is the Class A address. 10 is interesting because 10 actually was used. It belonged to the US military. It was called MILNet, aka US military network. But they don't use the the 10 dot addresses anymore. So a 10 dot address gives you 24 bits of addressing, and that's large enough for pretty much every organization on the planet. When you set up your NAT system, you set up your IP gateway to your ISP, you normally will find that that's a function that's built into that gateway. So you're going to give it an IP address range to use for the machines inside of the network. And normally you'll choose one of those three, a 10 dot or a 172 or a 192.168. So that's all we're talking about. We're just talking about using these abstractions and these namespaces to separate the pieces that we're working with in a way that allows us to extend them far beyond what we ever envisioned was possible. I should put a chair there so I don't walk near it, because it's like this big, gooey, smelly, disgusting pile of hand sanitizer. Maybe it's shampoo. I don't know. It's something scented. In some ways, the techniques we've used with sharding are one of the models that we can use for doing these kinds of overlays. So we built a larger namespace. So when we talk about sharding, we usually think of it going the other direction, which is we take this big key value store and we then split it up into pieces. But a different way of thinking of it is to say that as long as I have different disjoint pieces and I can glue them together and end up with something larger, well, okay, it's kind of like half full, half empty. It's the same thing. Oh, I missed one point there. I do want to at least point out. So we do have to keep track of these things if they're going to give any dynamic support to them. This was design project 3 in spades, is what do you do when things change? When you decide you're going to add another shard group, when you decide that you need to replicate, that wasn't design project 3, but we've talked about georeplication and how that makes things a lot more complicated. How you deal with failures. Gee, we're back to failure again. The last point is actually the one that I felt like I wanted to mention here, which is one of the benefits of having these disjoint domains is they can be administered separately. So the point is that once it gets to your router, what goes on inside of your organization, nobody else needs to know. As far as they're concerned, you're just that router. You got one IP address, and everything internally is getting mapped onto that one publicly visible IP address. That's a sharding mechanism. We're hiding a lot of the details, and no one really cares. We need to have strong support for communications, for the ability to communicate, to talk across these nodes, to do this in a way that provides us with the ability not just to send messages to each other, but to broadcast things or to multicast things. I mean, broadcast is just the general case of multicast where everybody gets the message. I always thought multicast was really cool. Some of that was because, of course, I was biased. I was working with the guy who did IP multicast, and it's still in the protocol, right? That IP actually does still support IP multicast. It's just not very heavily used, it turns out. So sometimes really cool features just don't quite get used as much as you like. But that's fine. A MapReduce style interconnect. We need barriers. We need ways of making sure that we order operations. What we use barriers for, to provide causality or ordering. In essence, that's what we did with Paxos. We created a barrier type system, right? We spewed in a bunch of messages and out came a linearized version of those messages. And we did that using barriers. We use atomics, compare and swap. That's a very common one. I've used that one myself quite a lot. I don't have any on me. I'm not going to touch you. I use that one quite a lot myself because you can perform an operation without a lock. You can say, I'm going to read something in, I'm going to do some work based on that value, and then I'm going to do an update. But as part of that, I'm going to say, only do it if that value hasn't changed. It's literally a compare and swap operation, which says, if these two things are the same, switch it to this other thing. Typically, we do that in hardware. You can do it in software. There's nothing that prevents you from doing it in software with like a mutex. But hardware can do this extremely efficiently. And it's a common thing to show up in CPUs. Let's see. Timing, okay. RDMA. RDMA is a fun one. If you took 313 or its equivalent, I think there's an ECE equivalent. You'll know a little bit about computer architecture. You should maybe remember what direct memory access is. That's where peripheral devices can access the RAM in the computer. In RDMA, one computer accesses the memory of another computer through the network card. So the network card actually has DMA access, and then it exports the interface to that memory on the local machine using what's called a remote DMA interface. It's actually pretty cool. It is a very interesting high-performance scaling technique for moving data between different computer systems without involving the CPU itself. I've spent a lot of time talking about key value stores. The last I looked, and I haven't seen anybody crowing about a faster one, the last I looked, the fastest key value store was a key value store that Microsoft had built using network cards with RDMA, and they directly inserted elements into the key value store through the RDMA interface. It was crazy fast, like 150 million key operations a second. 150 million. There are also things like direct cache injection, where you directly tell another machine what it should actually put in its cache, rather than have it discover it. All of these are peculiar techniques that do end up getting used because they help us build very fast networks. And networks are pushing the edge of the envelope here. We are now working on 800 gigabit per second network cards. That's the speed of a memory bus. That's 100 gigabytes per second. It's literally as fast as memory buses run. So what ends up happening now is we end up building these systems, and these systems look pretty much like multiprocessor computers. See, there's this kind of bias when we talk about networks. We tend to think of them as kind of slow, higher latency, lower bandwidth. Yeah, okay, well, latency is kind of an interesting issue, and there are people who are working on that. There's this big push recently in the research community to do optical computing. And one reason is because the speed of, look, I actually happen to have C on the board, coincidentally. It's an esoteric fact. The speed of light in a vacuum is the fastest anything can travel. That is the fastest rate at which information can travel in the universe. Does anyone know what the speed of light is in a piece of copper? Really, the speed of electrons in copper wire. It's about 2/3 of the speed of light in a vacuum. So if we can do this optically, we get a 50% increase because it's 2/3, half again as much. 50% increase over what we get with traditional copper wire. That's a big deal. Like, holy moly, imagine that somebody handed you a car and said, this car will go 50% faster than it can now. You'd be like, cool, this is great. Yeah. Oh, the CPU too. Oh yeah. They have the optical equivalent of transistors. Oh yeah. I mean, it's electrons and photons aren't really all that far apart. Electrons weigh slightly more than photons because photons don't weigh anything, maybe. But so they act a lot alike, which is what makes them kind of interesting. Why we can have flow of electrons through copper wire and whatnot. But this isn't a physics class, and I'm not qualified to speculate further. Yes? What do you mean, why hasn't it been done yet? We are doing it. I mean, I literally live in a building where they decided they had to replace my telephone service because they needed to put another fiber optic cable into my apartment. I already had fiber optic cable in my apartment, but they decided they needed to use another one because they didn't want the last, I don't know, 25 meters be copper. It's very weird. So yeah, no, I mean, that is literally what happens. Almost all of the internet backbone now has been fiber optic cable for a long time. And there's different kinds of fiber optic cable, right? There's the cheap fiber optic cable, which is multi-mode, that you have to put a repeater in about every couple kilometers. And then there's single mode fiber, which is really expensive, but you can put those repeaters in like every 50 to 100 kilometers. And they are faster. They're notably faster. There's a book that I've mentioned before called Flash Boys, where they were talking about building high-speed networks between New York and Chicago so they could front-run orders in the stock market. You place an order, and I would see that you placed an order, and I would have a faster route to get my messages. Literally, my network packets could get faster to the market. I could buy up what you were trying to buy before your order got there, and then I could sell it to you at a higher price than what I bought it for. And we were talking about milliseconds difference. And somebody figured out that they could use like microwave relays, and then someone else decided they were going to put fibers in, and the fibers end up basically winning. But even there, the fiber, the path the fiber takes can make a difference. Wow. 2 more kilometers of distance makes some amount of difference. Well, kilometers isn't a lot, but it does make, these things add up. And each time you have a relay, you have to reboost the signal, it slows things down. Because that's not, you can't move and re-amplify the signal at the speed of light. You do get a little bit of slowdown every time you have to bump it up. So that's the reason people would spend a lot of money putting a single mode fiber in the ground, because it would give them the fastest path between Chicago for trading. It's that insane. Yeah. How big is the bandwidth of the optic fiber compared to the copper one? Optic fiber is significantly higher bandwidth than copper wire. So usually the graphics, I remember them doing when they first started using optical cables, you know, they use these big bundles of copper wire, and then it would just become this little tiny strand of optic fiber. I don't know what the exact ratio is, and I'm sure it's changed. But they are very, very good at packing a lot of data. We still have a bandwidth limitation. So we still have to worry about the bandwidth. And of course, we still have a latency concern. That's why, you remember I talked about the speed of the bandwidth of a van full of hard drives versus the bandwidth of the internet. A van full of hard drives can drive from one side of the continent to the other side of the continent and have higher bandwidth than we still can get from all the fiber optic cables we have. Because much of this is implemented in hardware, we end up using algorithms that allow us to scale up efficiently in hardware. Hardware isn't good at everything. Hardware is good at certain kinds of things. So we end up picking approaches that are generally scalable. In peer-to-peer systems, so the next couple of lectures are a lot more about data centers, because this is a big area of consideration in distributed systems. How do we build out data centers? Why are we building all these replicated databases in the first place? You will hear some of these terms if you start working with people who are familiar with data center terminology. They have racks. Literally, these racks are pre-built, and they are then brought in on a forklift and put into a data center. Boom, boom, boom. And they'll often have the entire bundle of cables come out. Everything will be labeled. It will all be inserted and attached. Because if something doesn't work, nobody's going to track it down and figure out why it doesn't work. They'll just let that component fail. These things are built for redundancy. They are literally built expecting that some of those pieces are going to fail over the lifetime of that rack. When enough of the components in that rack have failed, the rack will be brought out of service, and that forklift will come back. They will disconnect all the cables. They will take the rack out, and it will go back to a facility at some place where it will be disassembled, salvaged, and rebuilt. A company I was mentioning before that used to build the big PCs, 32 core or 32 processor PCs, which at the time was the biggest you could get, and these were millions of dollars. One of their big businesses today is, in fact, maintaining these racks. They build the racks to order, they install the racks, and they maintain them, which usually means pulling them out when they're dead. So in a rack, we have a set of servers. At the top of that set of servers on that rack, we have what is called the top of rack switch, or the TOR switch. A TOR switch is generally a very high performance switch that connects all of those servers together and then has larger, high bandwidth. It's almost gone at this point. I've managed to pick it all up. There's a little tiny puddle left there. There's a larger, high bandwidth interconnects to other locations in the data center. Those are aggregate switches. Aggregate switches connect multiple top of rack switches together and in turn have very high switching speeds, very high capacities, and they are a lot of money. I mean, you've got a router at home, right? Everybody's got one sitting someplace in some closet. Maybe it belongs to TELUS or Shaw or, I don't know, one of the cheap carriers. It's not that complicated. It's a pretty small device. But in essence, it's doing the same basic thing, right? It is, and it's doing it over copper. Maybe it's doing over fiber. Fiber is a little more expensive. When you start looking at these aggregate switches, it is very interesting to look at them and to say, wow, this has 32 optical transceivers in it, and each of those optical transceivers is $30,000. Oh yeah, they can be quite expensive. They are very complex, sophisticated pieces of equipment. Yes, there's a lot less heat dissipation with optical, which is one of the other reasons why they like using it. Typically, as you start moving up these switches, you'll see that they all move to optical. Optical is faster. Optical has, there's no EM interference from optical, which is nice as you start packing more EM cables together. I don't know if you've actually looked at Cat6 and Cat7 cables, but the place that Cat6 and Cat7 cables start to fail usually is in the connectors, because below that, they have very specific twisting patterns that they use in the wires to make sure that they don't get EM interference, but eventually you have to put a connector on it. And it's in the connectors, when people start unwinding them, that you end up with problems. So it wasn't as big a deal when the bandwidths were lower, but when the bandwidths get higher, these things actually radiate EM signals that will interfere with transmission. So you have to know, people don't do these things by hand these days. It's all done with machines because we need that high level of precision to make sure that we're not getting that crosstalk. So guess what? Optics solves that problem. There's lots and lots and lots of peer-to-peer systems out there. We've talked about Bitcoin. We didn't talk about BitTorrent. I don't know why Tor is on here, but we have, anybody use Tor? He's probably running his own Tor, output node. That's how people, do all sorts of illicit, unlawful things. You have to be super careful because it's still very easy to compromise your privacy even with Tor. But yes. I mean, that's how you get to the dark web, right? Not that I would know. It was strictly a research project. When I was bored, and I was taking this class on cyber physical security, and then we learned about things like the fact that there's this website called showdown.io, and it just scans the internet and looks for holes. So like you can put your own IP address in there, and it will tell you what kind of router you're running and what ports are available. And what's kind of cool about it is you can then say, oh, great, show me all the Mongo databases that are using the default password. Oh, yeah. There's some pretty cool Mongo databases out there that are using the default password. This was well known 5-6 years ago. Most people have been slapped enough that they're not doing that anymore. But it turns out there's still a lot of interesting places where people put their traffic lights on the internet. And you can just upload the DLC code. That's kind of cool. That traffic light's no longer going to behave well, is it? What do you do when you're bored and you're on break and you don't actually want to do any work, but you don't really feel like playing that game because it's too easy? You reprogram Malaysian traffic lights. You guys laugh. I was talking to somebody in South Carolina who said, yeah, they did that in our town too. And I'm like, what? Why would you put anything you cared about on the internet? Peer-to-peer literally spans the globe. I think that's probably why these were chosen. I didn't choose them. Somebody else chose them. I think that's why these were chosen, is that basically these are services that literally get used all over the place and that are used ubiquitously. So one of the interesting problems in peer-to-peer, and I know I talked about this before, is how do you actually find the right peer? Turns out locating your service is a hard problem. And we end up using a set of naming services to do this. So one of the most interesting naming services is the domain name service, which ends up being used in almost all of these solutions at some point or another. You might recall I talked about the DNS service as a failure of the day. CloudFront. You could have a centralized registry, but of course this doesn't work super well because you have a single point of failure. Okay, fine, we can replicate it. Then you still have to trust this one entity. I don't know about you, but I don't trust me, let alone the person who left this disgusting goo. And I know that they're involved in the internet. Napster. Does anybody remember Napster? I barely remember Napster. It was like 20 plus years ago. Yeah, well, that's how you used to download music. And then we discovered some Russian site that you could download music for like, 35 cents for a song. They got shut down too. They were licensing it to you under Russian copyright law. So in theory, it was actually legit. It's just that, of course, when you live in a North American country, north of Mexico, the rights holders want to extract as much money out of you as they possibly can. They know the Russians don't have that much money. Well, some of them don't have that much. So peer-to-peer, how do we find the right peer? We can use gossip protocols where we don't have a single point of failure, but we don't have a bound on the lookup time either because you just start basically talking to things you do know about and they tell you about what else is going on. So this is not centralized, but not terribly efficient in extreme cases. So Bitcoin is in fact a gossip-based protocol. It goes and it tries to find other Bitcoin nodes. And once it finds other Bitcoin nodes, they gossip about each other. They literally tell you, oh, here are the other nodes I'm talking to. And Nutella was kind of like Napster as well. One of the common approaches here, and I have mentioned CORD several times, one of the common approaches here is to use a distributed hash table. In a distributed hash table, we have a decentralized index, which gives us a probabilistic bound on lookup time. But doesn't have, so we're not centralized. We have a resiliency mechanism, and it scales really, really, really well. One of the downsides to doing centralized is while it's super easy to do, it doesn't scale particularly well because the more people hit it, the harder it gets, the slower it gets. And in Napster's case, the people who owned the music got upset, sued them, and put them out of business. So it basically said, don't centralize this kind of stuff. Chord is a really good example of that. Academia, I don't actually know what that is anymore. And Amazon has DynamoDB, which is a distributed hash. Not to be confused with Dynamo, which is another Amazon key value store. Did you have a question? Never mind. What is a distributed hash table? What is a hash function? Hash function takes some input string and gives you back some output string. Ideally, we use it to map into a fixed-sized range. It gives us a fixed-sized output string. Better. How big could that output string be? Well, a common hash function these days is SHA-256. And so the output string is 256 bits. That's 32 bytes. It's really useful for mapping names, variable length names into this uniform space with low collision rates. Frankly, a 256-bit hash value is a really big space, and we get really good scatter on it. We picked SHA-256 because it's a cryptographic hash function, so it definitely has lots of randomness in it. The best pseudo-random number generators we know about happen to be cryptographic algorithms, because a good cryptographic algorithm doesn't leave any trace of the original structure of the data. So it's literally noise. These days, that's very common. They'll use the AES implementation. Like the Intel processors all have AES instructions in them, so you can run the AES algorithm in software or in hardware, and it's very fast. You can get really good pseudo-random numbers. What's the difference between a random number and a pseudo-random number? One is deterministic, because you start with a seed, and it will always generate the same sequence of numbers, but the sequence of numbers it generates does not have a distinguishable pattern to it. A truly random number is not predictable. So for example, if you need a truly random number, a common source in a computer these days is thermal data in the processor itself. It turns out it's highly random, and it's not easily predicted. So there you go. But most of the time, that's not what you want or what you need. When you're doing simulations, what you really want is you want to have pseudo-random, because pseudo-random says, as long as I have the same seed, I can get exactly the same results. When you use real random numbers, good luck. Geiger counters create really good random numbers as well, because radioactive decay is a statistical but not uniform function. So take yourself some plutonium, plop it down, and use your Geiger counter as your random number generator. Cuddle up to it at night, because plutonium needs to be kept warm. Okay, so the idea is that you take an object, you run it through the hash function, and then you use that to scatter it to different locations, to different services in the network. Chord was this interesting distributed hash table that used SHA. Look at that. Used SHA checksums to take the key, hash the key, and then determine where it would fall in the ring. It used consistent hashing, but it used consistent hashing and then added on a routing table. And the reason for that was because the downside to consistent hashing is we can't easily deal with hotspots. If too many of the hotkeys end up in one of the nodes on the ring, things get slow. So what they did was they said, this is like a systems trick. Why do anything directly when we can do it through a table lookup? So instead of actually getting to the key, what we do is we get to a table that says, here's where the key is currently located. And thus you could move keys around in order to load balance, in order to make sure the hotkeys were specially cared for and uniformly distributed in order to get better load balancing. Remember in Design Project 3, they moved entire shard sets. This is down to the level of individual keys. What ends up happening, in fact, is most of the time you just leave the individual keys exactly where they should go. So you don't have an extra hop. The only time you have an extra hop is when we've moved that because this thing is hot, 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 baby, and we need to put it someplace else that can handle the load. So it becomes a trick for load balancing that occasionally causes us to have an extra hop. Yes. So Cord uses a consistent hashing scheme, but it adds a routing layer. So the consistent hashing goes to the individual nodes. And then in that individual node is a table that tells it where that key actually lives. It's built right. So this is a distributed hash table. And Cord went one step further, which says the distributed hash table isn't the actual keys. It's a routing table to the keys. Most of the time, the keys will happen to be on the node where the consistent hashing said it should be. But occasionally, it will route you to a different location. So you can get an extra level of load balancing. Okay, I'm trying to make sure I'm not missing anything. Right. So when we insert something, this is actually pretty easy because we just compute the SHA value of the key, and that tells us where it should be inserted. So what we do is we go to the node. Now you notice that not all the nodes are populated here. So we go to the node, and if the node is not present, then what we actually do is we go to the prior node until we find one that is present, and that's where the key goes. Oh, sorry, next node, not prior node. When we go to look up, we do the same thing. We go to where it should be. If there's a node there, then the node will actually know where the actual key is located. Otherwise, we'll have to look at the subsequent node to determine. So the question then is, can we actually improve this? Because this is an order in lookup. Worst case is we have to go through all of the nodes in the system. Can we do better than that? And these are the finger tables. This is actually routing information. So you go, and they keep routing information in each node of where things are. So think of it as little pieces of metadata that we're replicating across this. And this gives us order login. Now, why do I need login? How many nodes am I going to have in this system before login starts to make a difference? Because I can tell you from personal experience, when I build hash maps, I always put in linked lists. How many, because it's basically the same thing, right? It's how many things do I need to be hashing into distinct nodes before it becomes worth adding all of this extra complexity? A lot. Because, well, let's see. If I had 10 nodes, Log 2 of 10 is 4. So 10, 4, not a lot better. And I'm spending a lot of complexity there. So probably you're going to want to see at least 50, if not 100 nodes or more before it justifies adding this extra level of complexity here. Lots of factors go into that. I'm spitballing this at this point. Nothing is definitive here. You'd actually have to do the math. But it's pretty easy to look at this and to say, look, I wouldn't do this if I only had 10 nodes, because it's just not worth this extra complexity level that I'm putting in here in order to save 2 lookups, maybe. So we'd only use this kind of solution in extreme scaling conditions, when we really are trying to make this thing scale to hundreds, if not thousands, of nodes in our DHT. Cord actually is a really cool paper. It's a very interesting piece of work because it handles nodes appearing and disappearing. It handles redistributing data as the topology of the ring changes. We actually can get better performance by adding further metadata as well. Now, many of the performance guarantees here are probabilistic as opposed to worst case. So in worst cases, probably will still melt down in some weird-ass way to order n. But in the common case, it's like quicksort. Everybody knows that quicksort is the fastest sorting algorithm, except when it's not. Similar. Yeah, I would say that in some ways it's kind of the same basic sort of idea. You add some extra indexing to get you to where you want to go faster. And I did mention this isn't going to be on the final exam, but if you're into DHTs, this is definitely a really cool paper. So we just looked at this whole distributed gossipy network. A different way of doing decomposition is to actually have a hierarchical decomposition. So we do have master nodes, but then they relegate things to submaster nodes. I guess master is not cool anymore. So primary, secondary, tertiary, quaternary, quaternary, so on and so forth. The downside to hierarchical design is that at some point it doesn't scale either. I know that. I work with file systems, and I can tell you that file systems that have 400,000 directories, like my personal laptop, that one, I indexed it, had 400,000 directories, just in my personal directory, and 2.7 million files. Yeah, that's a big old complicated mess where I can't find anything. I mean, I'm in this research because I can't find things. How dare they vacuum? It's very noisy. Let's hope they don't unplug the server in order to plug the vacuum in. I wish I could say that wasn't an actual failure case that I've read, but I have read it more than once, where some small outfit would have server outages on a regular basis and they never figure out why. And then finally somebody like set up a camera and figured out that it was the cleaning lady unplugging the server because it was the only place to plug the vacuum in. And then they plugged it back in. So communications costs are a big issue here. Maintenance costs, when you start doing these overlays and whatnot, become important to consider as well. But one thing to keep in mind is that nodes have different properties. We have point-to-point communications. Your cell phone has a point-to-point communications with the cell tower. We have stability issues. We have mobility issues because I was using cell phones. I keep using cell phones. How do cell phones know to switch when you move from one cell to another? There's a whole protocol around doing handoff. Because at some point you realize you're in the middle and they can both talk to you. And they have to agree on which one is your primary point of contact. And you don't even think about this stuff. How many nodes are there? What are the communications patterns? As we get richer and richer networks, these things become more complicated. So we have large-scale data centers. These data centers are huge. I've literally thrown out big numbers, and yet it's not uncommon for people to talk about spending $1 billion building out a data center. They are huge capital investments. How many of you have ever used cloud computing services? Dropbox, Google Drive, OneDrive, iCloud. Right. They're all data centers. They're all living someplace in data centers. Your data is living in multiple data centers in replicated harmony. Probably on top of someone's crappy Paxos implementation. Let's hope it's not one of the students in this class who wrote that. If so, maybe you'll get your data back. Wide area presents a different set of challenges than local area. And when you start talking to people about these things, you realize they create all sorts of different terms. We have local area networks, we have wide area networks, we have metropolitan area networks, we have geo-replicated networks. Ah! And then, of course, I come along and suggest that we need to have a lunar data center. So now we have it's not even a terrestrial network. Now it's right, well, you can argue that the moon is part of our planetary system, but what happens when we decide to move, we put one on Mars, right? Because there's water on Mars. Ooh, we can build a data center there. I mean, I like those examples because those examples help you really think about what issues happen at those scale. It's the same set of issues that happen when it's the network is here at UBC versus the network is here and in Toronto. We have a much higher propagation delay for things that happen in Toronto. But when you make it the moon or you make it Mars, it's so large that our brains don't sit there and going, well, you know, it's less than 100 milliseconds, so it doesn't matter because I can't see it when I'm gaming. If your game server is on the moon, you will see it. And your brain knows that. Or you can convince your brain to know that. Anybody heard about the Voyager space probes? How many hours away is it now? It's like 36 or something. It might be a round trip, but it takes hours and hours for us to get signals back from these. And yet we still manage to do it. And these are things that were built in the 1970s, before you were built. Pretty cool what we've been able to do, even with very primitive networks. So in mobile networks, we have mobile support stations and mobile hosts, and those tie into wired networks, which then talk to traditional fixed hosts on standard networks. And this, of course, is how we tie mobile networks to data centers, to our home network, and so on and so forth. And this all ends up working together seamlessly. It's just magic, right? Except that you're going to go out after taking this class, and you're going to be building some of that magic. You will become one of the magicians. Mobile hosts are really cool because they're mobile. Ooh, that's deep, isn't it? Lower speed mobile networks. So, you know, it turns out that not everybody gets LTE speed. How many of you are running on 6G? None of you. It's still in development. But it is in development. People are actively working on 6G services. Battery power is a huge concern because the stronger I make my signal, the more power I consume doing it. And so I get a better signal, but I don't get as much battery life. It's like me and my laptop, a gaming laptop with a 3080 in it. the battery is not long for this planet. It's a little bit longer than a cheap UPS. So when somebody tries to send a message to your mobile device, they need to figure out where you are quickly. So we need to have fast lookup of the mobile host, which means we need low overhead in our overlay so that we can get the information we need as fast as possible. Since these nodes are themselves different, they also have different concerns. We don't have a uniform set of devices because, my gosh, my toaster is on the internet now. My battery-powered toaster. I mean, we laugh, but our cars are on the internet, our toasters are on the internet, our light bulbs are on the internet. Some of those things actually are directly wired, so that maybe doesn't count. But our phones are on the internet. Maybe you have a tablet that's on the internet, or your computer has a mobile access. Cars certainly do. It's almost impossible to buy a car now without some sort of monitoring on it. Maybe you have air tags or you have tiles. You can track down your devices when you misplace them. Tons and tons of different kinds of nodes. Each of these then requires that we use different algorithms for optimizing for the particular behavior we need in those particular cases. How much does it cost for us to find things? How much does it cost for us to change our state? Remember, if we start replicating state, there's a cost associated with replicating. So how are we going to balance that out? You don't want to end up. So this is, we've been talking about databases, and we tend to think of our key value stores as being these sort of fixed things that are identical here. But could you imagine that what you actually have is a portion of the database replicated here? And that over time, you move responsibility for pieces to other servers as you don't care anymore because that mobile device hasn't been in your neighborhood for the last 24 hours. Makes perfect sense. Why would you want to maintain state for something that you're not using right now? Somebody else has it. When it comes back into your range, then you can pay the higher price of going and fetching a current copy of that state. But rather than keep stale data, you toss it. Perfectly reasonable. So when you're analyzing these things, you have to look at what the cost is associated with wireless versus fixed devices, and the costs associated with the mobile host versus the mobile substation, i.e. the cellular network itself. And what kinds of costs do we have to worry about? Well, the cost of search is based upon some function of the cost associated with the mobile host and the cost of the wireless network itself. So the more accurate things are, the more expensive it becomes. The less accurate they are, the more likely it is that the network is going to have to forward packets. We can go to a tiered hierarchical structure, in which case then we put the support stations in the logical ring, and the support stations know about the hosts that are in their particular cell. Oops, well, you didn't need that phone, did you? You were wanting a new one anyway, I know it. So the cost here of the search now becomes a function of the mobile substations and the fixed devices. And so that's a completely different set of trade-offs now. We get a completely different performance model. And it turns out that algorithm 2 is a much better way of doing this. So what we end up doing is putting most of the work on the mobile substations and in the fixed portion of the network, because they don't have the same cost structure that the mobile hosts do, the device that used to work that's now on the floor. It's probably still working. Mobility support costs are different. So when do we actually update our state? Well, So the mobile service, mobile substation, searches for a new mobile substation when it needs to, but doesn't do it proactively. So you don't go looking for information until you actually need it. Where is this device? And so you propagate through the network and you say, how do I reach this device? And you can see how this ends up building into this whole hierarchical model. Like when you call my phone and your carrier has its own set of these algorithms, and then it has to contact some central repository of information that says this belongs to so-and-so, and then it transfers the call information over to my carrier, and then my carrier figures out where my device is currently located, and then it rings because we've managed to set up a connection between these two. And we didn't actually have to involve the mobile devices themselves in that. It was all done in the network. And this is why you can literally be standing in a cafe in Paris and get a phone call from your mother who's in Dubai seamlessly. How hard could this possibly be? Pretty cool. I mean, this is what we end up using these distributed databases for. But this is an interesting take on these distributed databases where there's a lot of dynamic behavior going on in this system, and we don't want to remember everything in every place. We're no longer replicating complete data. Now we're replicating portions of that data. And now we have to think about this in a different way. So different algorithm. Mobile substation informs the original mobile substation each time a new mobile host joins. This is more expensive because it's based upon the number of moves. How often do devices move? If they don't move very often, maybe that's the right one to use. If they move frequently, then algorithm 1 is probably a better choice. There you go. So a little introduction to peer-to-peer and mobile and how that overlaps with distributed systems. So the person I work with at Georgia Tech does a lot of work in mobility, mobile systems. Why? Stealing these slides from her. Worked well. She literally has researchers who were working on 5G before it was a real thing, and now they are working on 6G as well. Yeah, whole amazing set of interesting, challenging, complex issues where increasingly, in order to meet the latency requirements of 6G, a lot of the services end up moving all the way out to those mobile substations. But mobile substations have a lot of limitations in what they're able to do. So we don't replicate everything to the mobile substation. Instead, it becomes like a temporary replica. While I need this information, I can keep it up to date through the fixed network. But when your device moseys on because you're not in Paris anymore, now you've moved on to, I don't know, Zurich, because you felt like you wanted to go boating. Have you been to Zurich? So the first time I was in Zurich, I was there for a SIGCOM meeting, special interest group on network communications, and they literally did a boat ride out on Lake Zurich. It's beautiful. Absolutely beautiful place. It's one of the most expensive places to live in the world, but so is Vancouver. So, and I don't know, has anybody been to Zurich before? It's an amazing city. You can spend $20 here too. Well, if you spend $20 in Tim Hortons coffee in Zurich, then I can understand why you might not want to go back. Holy shit. Guess what? He was in a touristy area. My advice when you travel, don't spend too much time in touristy areas. You know, you get into a touristy area, this is one of my rules of thumb. This is esoteric knowledge. You get into a touristy area, you need to find a place to eat. Choose some place that's on the second floor or the basement. You know why? Tourists are lazy. They will go to the places that are on the street level. The only way you survive on the second floor or in the basement is if you're actually decent, because the locals will actually walk up the stairs or down the stairs to go to good food rather than eat the shit that's on the street. It's a little bit of an oversimplification, but it turns out it works in a. So There you go. The coffee shop upstairs would have been half the price. Fair enough. There you go. Well, it's like sitting at the Florian restaurant in San Marcos Square. You feel like you're in the middle of a James Bond movie, assuming the water isn't up around your ankles. Does anybody have an idea what I'm talking about? A couple of people obviously do. Where is San Marcos Square? It's in Venice. And it's James Bondish because it's the big open square where, like they have races, they're always doing things there, like chasing people through it. I haven't been there in 20 years. Sorry? Yeah, totally. I mean, like they're going down the Grand Canal and the whole 9 yards. It's great. Venice is awesome. Anybody have questions? 42. Point-to-point microwave links, yes. Yeah, they totally do that kind of thing. But then it turns out that fiber optic cables are faster than microwave. That's what they do. Yes. And there are people who sell those to you for very high prices because literally front-running orders is big business. It's kind of frowned upon, but it is big business. Because that way you can put 6 fibers in the ground and sell them to 6 different companies. Get them to bid off against it. The biggest problem in those, or the biggest challenge, is actually getting the right-of-ways to put those cables in the ground in the first place. Because so when you do microwave relays, it's not as hard because you don't actually need to get a license for anything between the 2 points. But propagation delay, again, it's your speed of light through atmosphere is slower than the speed of light through vacuum. Actually, the speed of light in glass is slower than the speed of light through a vacuum too. So you have to compare that. I don't know exactly which one's faster, but I have read about, yes, because the Flash Boys, they actually did that between, I think it was the Chicago Board of Trade and New York. And they were front-running orders. Yeah, it's really cool. When you first sit down and you read that, you're like, what? People actually do this? And yes, the answer is people actually do these sorts of things because large sums of money are involved. And when large sums of money are involved, it is your moral responsibility to absorb as much of it as possible. Oh, sorry, that's the consultant in me talking. I can absorb up to 10 times my excess weight in cash. That's why I need this. Any other questions? Yes, question there. How does peer-to-peer work behind NAT? So that's actually really interesting because peers trying to connect through a NAT gateway generally can't easily do that. And so there are a number of tricks that you have to use. So for example, you can leave a connection open. You can set, when I SSH to my NAT, to my router at home, that IP port or that TCP port gets forwarded to a particular machine. So, right, yeah. So there are a number of different ways of doing three-way handshaking to get those things set up as well. But a lot of times, that's why you can't set up peer-to-peer through a firewall, because there's no easy way for them to set up that connection. The more interesting tricks become when you start using connectionless protocols. So for example, you send packets out on a UDP port. UDP packet comes back. How does the gateway get that UDP packet back to you? And again, you can use the same kind of scheme. Pre-register it. Or you can have a protocol. I'm pretty sure there's some protocols. I've not spent a huge amount of time looking at this. Bats? Large ones? I knew we had a rat problem here. I realized they'd gotten that. Cool. For those of you who are listening to the stream, we hear this large booming noise in the background that sounded like a drum, large drum. So there are some techniques, but it is actually a complicating factor in this kind of work. With TCP, it's not as hard because you can actually set up the TCP connection, and part of the TCP connection trains your NAT gateway on what the connection port is. But getting a connection to come back in and then get connected to you, that's where you still have to have some sort of a negotiation protocol with the NAT gateway itself in order to set that up properly. Yes. Yeah, they have to have a handshake protocol in order to be able to set up the two streams that you can get because the end streams, because they're pulling data down from you. So I think what you do there is you set up an initial connection. I'm guessing here. So go look at the BitTorrent code if you really want to know. You set up the initial connection to a BitTorrent server that's on a public network, and then they tell you that they want to connect to you, so you connect to them and you tell them the port that you're using, and that way they can then hand that off to someone else, and that someone else can then talk to you. Yeah, you end up doing some sort of a proxy to figure out how you're going to set up that connection. Yeah. Three-way handshaking at its finest. Because we'll take TCP, which already has a crappy three-way handshake, and put another handshake layer on top of that. It's like cake. One layer is good, two is better. Three, now we're talking. Edge computing in general involves devices like mobile phones, but also VR goggles or any other device that literally sits on the edge of the network, typically mobility devices, yes. So 6G's concerns are about how do we enhance our ability to support edge computing devices. Because what's happening is we're moving more and more of the compute closer to these mobile substations, because the mobile substations then are where you want to, or near the mobile substations are where you want to run those services. In the end, what happens is they move them all the way to the mobile substations because that decreases the amount of latency and improves the service that you can provide to the edge device. This is why there's a lot of research going on here. How do you actually run containers on these mobile substations? So they build container models. They build little models where things literally run on either right next to or in the mobile substations themselves. So think of it as like, instead of having big data centers, you have little data centers. All right. Well, then we're done. And there is no self-assessment again on this, so don't worry about it. Next couple of lectures are going to be like that. I have one. I'm not sure if I'll do include it or not. But we're going to have more topics like this. Kind of wander around a little bit and talk about some of the other things in distributed. So have fun finishing up your DP3 peer review. What's due tonight? Something's due. Sorry? Right, exactly. I think the DP3 peer review is due at 11:59 p.m. tonight. But so my expectation, part of the reason I'm doing it this way is because I expect that you're going to be spending more time on capstone. I'm getting some capstone questions, mostly because people are freaking out about, oh, well, was it today somebody said, well, I've looked at all these I came up with all these interesting ideas, and then I look and I find somebody's already done them, and I'm like, okay, it doesn't matter. The purpose of the capstone project isn't for you to create something that you're going to present as your PhD work. Something novel, a new contribution. The purpose of that is to help you go through your own design cycle now with your own project and say, I want to do this. Here's how I think I should do it. Here, I'm going to actually try to do it. Here, I'm going to figure out what I screwed up and how I can do better next time. That's the learning opportunity here. Get used to taking amorphous problems, and it's nothing more amorphous than a problem like this where you have to pick it, taking an amorphous problem, making it concrete, designing a solution to it, testing your design, and then saying, I need to iterate through that design. I need to do better. Or maybe you're going to be one of those people who says, actually, my design was rock solid. 2 weeks, I implemented this whole thing. It's now an open source project that everybody's using. There's no pressure to do that because that's not an expectation. If anybody does that, I will be astounded. I don't want to discourage you from doing that. But my point is, the learning exercise here is about using the tools that we've been talking about in this class to solve problems. So pick a problem where the tools are useful, break it down, show how you'd use those tools, explain how you're going to test your design, implement enough of the code to convince yourself that either A, you did a pretty good job of the design, or more likely, B, there's an awful lot of holes in your design, and this is how you would plug them. Now you've learned something. Now you can be like the student whose company has his database melting down, and you can step in there and you can go, I think I know how I would work on that. Because that's what's going to happen in the real world. All right, see you on Tuesday. I don't even know what day it is anymore. Wow, applause. I'm not used to that. They were clapping. Like, wow, I'm not used to that. Let me stop the stream, stop the recording, and then I will stop the stream,